chapters, with the exclusion of one little topic that I'll go over. But I want to finish up chapter 3 first, and then as time allows, and I think we'll have plenty of time until the first test, which is pre-scheduled for not this Friday, next Friday. So there should be plenty of time to read. So this class, the way that I teach is really interactive. I ask questions, and then you raise your hand, you answer the question correctly, you get a point. All of those will be bonuses, accounting for 3% bonus. So let's say if you answer 100 questions correctly, you get 100 points, and that will be 3% bonus. So basically the course will be 103 basically out of, basic for the course. So take advantage of it. It's easy to really get the 100 points. So for your reference, the first session, the first class earlier, majority of the people got 2, 4, 6, 8, 10, 11 points already, for instance. So it's really doable. So pull up your calculator, have it ready. I ask a question sometimes, do this calculation, do that, and then show it to me, and I'll give you a point like that. But before that, let me remind you of the policy. So I believe Professor Mowahed went over it. This is in-person class. One of you simply asked regarding a friend. No class on Blackboard unless we're told by the school. It's not my decision. The class is in person per the school's policy. But like last session, that we had to switch to online just because of weather situation, then we do that. Otherwise in person. So make sure you're attending classes in person, and it's about 45% or 35%, I don't remember, everything is in Blackboard. So we'll go with that. For any reason you have to be absent, you're allowed to be absent for 2 sessions, otherwise it will be failure, unless you have an excuse reason, and then you should really provide a letter. If you email me and then say, I'm gonna really be absent, I'm not feeling well, it's not about trust, it's about policy. You should provide a letter. Let's say from your physician for that day. Then I'll be able to put excuse. If you attending some conference because of school or because of a club, any club that you're part of, give me a letter from your advisor. We go from there. That's the policy of this course. And I want to be fair to everybody. It's not about liking person or not. Then really we go from there. For any reason, you want to be absent, make sure you provide a letter. This particular session, because it's the first class that I'm attending, if people are late, it's fine, but starting next class, I'll be recording the time. If you're late, then I'll go with the policy. Just be mindful of it, that I come from another city. It takes me a while. I have to wake up early and then get rid of all that snow from the car and then come in. I understand the same thing for you perhaps. But be mindful of it, that there's a policy and I have to be fair to everybody, especially those that come in class on time and do their work, they get their reward. All right, that said, we want to talk about a new topic from chapter 3. I want to make sure that everybody's on the same page. Yes, thank you so much. Please have everybody put the name there and then pass it to me so that I call your name and then give you the point as you answer the questions. So let's do a quick review. From the first 2 chapters that Professor Mowahed went over, what you remember. In particular, just name the stress types. One stress type that you learned. Please.
Stress. Shear stress.
What stress? Shear stress. All right. Actually, if you can give me a little bit of time, because I want to give you a point on that list. Maybe I have to give you more time. Yeah, just finish it, please, and give that to me. So shear stress is one of them. There are other stress types. Prepare those, please. And down the road, I want to also ask you for the equations for those. So prepare those until I get that list. So for the test, you'll be able to bring in one A4 sized equation sheet. Just fill up one side with equations, no worked out examples. And per the experience, students told me this. They wished they prepared better equation sheet. So I suggest as we go over new equations, write them right now. It's just the best practice. That way you do not miss any equation. I did print the class roster, but for some reason I forgot to bring it. It was not in that file that I bring. So today I'll take advantage of this, but next time we'll go over the roster. I remember, I see many familiar faces. Very good. Very good. Last row, if you get there.
Thank you.
It's heavy. Yeah. All right, thank you. Yes, I do remember you, but please remind me your name. Tyler, family name starts with? Leschuk, yes, a point to you. Shear stress is one of them. What other stress type you learn?
Normal stress.
Normal stress, your name please? Drew, family name starts with? L? Drew L. Drew L, that is, it's easy to find that way. Drew, yes. How do you pronounce it? Linema? Linema. All right, a point to you. So shear stress, normal stress. All right, then give me please the equation for each one of them. Yes.
For normal stress, is it force over area?
When we say equation, it has two sides. The left side,
Oh, is
the Greek letter, I saw your hand, sigma.
Yeah.
Sigma, your name please?
Archambault
Uh,
or Braden Archambault?
Braden, yes, I saw that, a point to you. Shear stress equation, yes, up there.
That would be
Tau, it is.
tau equals V over A.
V over A, the shear force, and your name please?
Nathan Schaffner.
Nathan, is it C, starts with C?
Starts with S.
S.
Say Joe,
Oh, I saw that. All right, very good. All right, so if you look at the two equations, they both start with force in the numerator. What's the difference? Yes,
The axis for the normal force is perpendicular. and
very good,
For the shear force,
very good. Your name?
Mohammed Wasi.
Mohammed Wasi.
Long.
You wrote it as Mohammed?
Yeah.
Let me see.
I'm gonna go by Wasi.
Yeah, but what you wrote, I
Yeah,
want to,
Mohammed.
Mohammed, yeah, I want to go with your name that you wrote down in here. Mohammed, yes. All right, a point to you. Yes. All right, so there are two differences there. First is the force, the other one is the area, as Mohammed says. So the force is, so what's the meaning of normal in that sense? So in mathematics, normal has two meanings, at least a few meanings. One of them is the opposite of abnormal that we learned. The other one is perpendicular. When we say normal, if something is normal to the other one, that means geometrically it's perpendicular. So that's why we call it normal stress. So we pull or push on an object, the force, you pull on it, the force is perpendicular to the cross section. So the force is like this, cross section is like this. So we call it normal stress for that reason. So shear stress is opposite. Open question, guys. How would you apply shear stress? So this is the object. You said if you want to answer?
Oh, no, go.
No? Yes or no? I saw your hand. Do you want to answer or no?
You say your first question, then after. But do you want me say whatever you're gonna say, then I answer at
Yeah,
the
the
end.
question is this. How would you apply shear stress to this?
You basically cut it in half, and you will put two forces on the side, and
I think I got your idea.
yeah, I'm not.
I got your idea. So one way is this. You put this object on this and then cut it like this. We call it shear stress. It acts like a shear, not EA, but the double E shear, the scissors. So the two are parallel to each other. So if you put an object in here and then you cut it like this, like a press, you're applying cutting at that common surface that you see. So we call it shear stress. That's one way. Or the other way is this. You put the two objects on top of each other, you glue them, you pull or push on one, so you're causing shear on that glue, the common surface. So we call it shear. That's the other one. All right, your name, please. The
Jesus.
last one then.
Moyoto.
This one?
Moyoto. Yeah.
Jesus, this one? Okay.
Jesus.
Okay, come to you.
Yep.
All right, so we learned those. Now the question is this. Why do we learn these? What's the objective of this course? Guys, it's really easy, I'll get back to you. It's really easy to make this course mathematically oriented, like what the textbook does. If you got a chance to take a look at it, it has big equations, long calculations, and then it gives you some number and that's it. You get really easily drowned by those big equations. But I want to avoid that. Instead, we want to have engineering discussions. As engineers, we have to be good at that, not just simply mathematics. All right? So what's the objective of this course that you think you got out of the first two sessions? Yes.
Behavior of solid bodies with external like stress.
Very good. One way of putting that. Your name, please.
Ethan Jackson.
Ethan Jackson should be up there. Yes. So, in fact, it's more than that. Our goal is this. As an engineer, you want to be able to comment on the mechanical safety of this object. Is it good under the external loading? So calculating the behavior is just a prelude to that. So once we calculated the behavior, we want to comment on whether this is good or not. To do that, then we have to be able to calculate shear stresses that we just talked about. By the way, I caught you. You want to say something?
I was going to say, to understand like when something would deform or maybe break apart.
I agree. I forgot your name.
Corollas. Corollas construction.
Yes. Thank you. All right. So then the question is, if mechanical safety is the point, then we have to answer this question. In how many ways mechanically can you damage, let's say, this particular object? Name those. Guys, be comfortable with me and this class. We're all one big team. I know a little and I do not know so many things, right? I'm a human being. Making mistake is human nature. That's fine. We try to make it correct by having a big team discussion. I'll go here and then to you. Yes.
The tip of the ballpoint pen. If it's too small, it falls through and the ink won't go. If it's too big, the ink won't fall. It won't write.
So mechanically, you say the size matters.
The size of the
All right,
ball
one way.
matters.
You make it too small or too big.
It won't.
You may load it too much and may break. All right.
Can you remind me what the question was? It was how many ways?
In how many ways you can damage this mechanically?
Does it count like just like breaking it in half?
Bending that you said, right? You showed me this. Bending is a subject of chapter 4 and on. It will be the second phase of this course after this one. Your name?
AJ Kennedy, last name.
Yes, I saw that. I saw that. I'm not sure about the order, but let's go from here.
You can twist it.
Twist is the subject of today. All right, so let me unfreeze this.
Be frozen.
All right. That's the subject of today. Your name?
Justin?
Justin, is that still, okay, remind me the family name?
Manor?
Should be, is it this one?
Yes.
All right, then go here. Squish it, like how?
Like, I mean, you can't, but, so if
I
that's
saw
other
that.
material.
Yeah, I want to make sure. So really, we have to understand this. Whether we do like this or like this, we're still in the realm of which stress type? Normal stress. That's why I want to really see how you're pushing it. So, Dozema?
Yeah.
Yeah, if you remember that. Jacob Dozema. Yeah, I point to you. And then, again, yes, I'll let you all answer that, yes.
You could crack the outer material
Crack, like how?
and apply strong enough normal force onto the surface in order to damage the outer.
So he said pushing, you're saying pulling. No, right? You're saying pulling.
I didn't say pull, I said push.
But push, how would crack?
Applying enough of a force onto.
Too much force.
to-
So you're not adding any new way of loading. You're just repeating him. Yes or no? Yes? Is that fair? I'll give you a point this time. But next time, please just make it a different case. Your name, please? Drew, family name? Lima. Okay, yes. All right, yes, please.
You can stretch it.
I do remember your name as well. So pushing, now you're talking about pulling, still in the real mode, normal stress, right? Gabe twist?
Yes.
Yes. All right, the point to you. And then yes.
Would a shear count as like a controlled pushing force, or is that different?
Yes, shear is one way of damaging it, right?
Yeah.
But show me how, I just went over that.
Yeah, like with a finger break or something?
Yeah. So one end is empty, you're shearing it, right? You're cutting it. Your name, please?
Great. You already watching?
Is it toward up here? Family, oh yes, I saw that. Is that Hecknan?
Yeah.
Yes? Okay. Thank you for being nice. All right, it's your handwriting, I cannot read. All right, 3 more, okay, yes.
Would puncturing be different, like if you have like a small circle?
Because you use a different word, but isn't that your, are you,
Like a needle or something puncturing?
no, I got it. So I want to answer that. So it's the combination of 2 things. You're pushing it, right? You're pushing it, and then you're also cutting it. It depends on that tip, right? The size. If you do with one little thing, something like this, and then on a big surface like this, you're cutting it. But if you do something big like this, then you're really pushing it. So it could be a combination of the 2.
Okay.
So because of that subtle point, I'll give you a point. Your name?
Francisco.
Francisco.
Should be close to the top.
Close to the top. Yes, the second one, actually. All right, one here. David Lazar, right?
What was that?
David Lazar?
Josiah Lazar.
Joseph, yes.
So could you like put something on one end to like, I don't know, bend is the right word to like almost.
Bending, it is
Like,
bending.
put it like that.
It is bending. We went more bending, I'll give you a point. I'll go there and then come back to you. Lazar, that means. Lazar, I have to find you. Where are you?
I think somewhere in like the middle.
Middle. Oh, yes. And if you said it already, let me move to another piece.
Sorry, what was the base of the question, forces? Or?
Damage it,
And
yes.
damage it?
Mechanical way.
And could we heat it with, like friction?
It's not mechanical, but because we talked about it, right? So yes, we talked about heating in this course as part of chapter 2. Remind me your name again.
Justin?
Justin, family name.
Manor?
Oh, that small thing, yes, it's there. Yes.
I wanted to add on to what Drew was saying about it cracking.
Mm-hmm.
That'd be an impact.
Impact,
Impact.
impact.
I couldn't say it clearly enough, so.
No worries, no worries. You were here to help, so it's good. Your name,
Braden,
family name, starts with
A,
A. So it should be somewhere here. Braden
Arshambo.
Ashambo, yes. If it's repeated, let's. I will not give you another point for that, but go for it.
Setting out a fire.
Set a fire. He was, yes.
Yeah, if heat counts, can we freeze it, make it really brittle?
Very good. It's the other way around.
Yeah.
But it's repeated, right? You said it. You said one already. There was one more up there.
Yeah, it was correct here.
What?
It was, heating it, so it was.
More saying.
Because the order, so many people here, you raise your hand earlier, I'll be fair to you, I'll give you a point. But remind me your name again?
Nathan John.
Nathan C. or S again?
SH.
SH. Oh, yes. All right. So nobody else. All right. So we went over the whole thing for this very reason. We want to be able to comment on mechanical safety. Then we have to be able to quantify those. All right. Some of you talked about heating. All right. Give me please the equation for thermal deflection equation. First come, first served. Yes,
Did you say thermal deformation?
yes, or deflection, the same thing.
Oh, so it would be delta,
Yes,
the fish-looking one. Alpha,
the
alpha.
very first letter you click, yes, alpha.
L and then parentheses T minus T.
Change in temperature.
Change in temperature.
Yes. Delta sub T for thermal equals alpha L delta T. I remind me your name again.
Braden.
The first few weeks I may need time. Is that Arshambo?
Arshambo, yeah.
Arshambo. All right. Yes. What's the name of that fish-like parameter? What's the
Alpha?
big name for it? Yes. Group.
The thermal coefficient,
Thermal expansion coefficient. Drew, is it dynamo? All right, very good. All right, that's a material property. For different materials, we have different alpha values. Experimentalists, we basically set up experiments to give us that value. They tend to be small values, really. Because mostly, let's say, metals will not really deflect or deform much with changing temperature. So that coefficient should be really small. All right, given those, anybody remembers any other material parameter from chapters 1 and 2 we learned? Like alpha was something about heating, but it was material property. Yes? Strain, it's not the material property. It's something that you measure, right? But for this material, it's this value. If you change the load, epsilon will change. Yes, up there.
Modulus of elasticity.
Very good. The letter, another person, so that another person gets the point. What's the letter associated with that? Yes? E, very good. Kathy, your name and your name. Let me see. Yeah, when I have the typed up list, it might be easier for me to spell it, please, for me.
REA.
REA. Is it toward middle up there?
It's like the middle bottom.
Middle. REA, right?
Yeah.
REA. It's the first name.
Yes.
REAGAN?
Yep.
And say it again. How do you pronounce it?
Reagan.
Right. Okay. All right, a point to you, and then yes, your name?
AJ Kennedy.
Yes, very good, a point to you. All right, E, we have a few names, yes.
There's another one.
Can I answer that?
Yeah.
Can I continue? So there are a few names for that. Any of those would work in this course, so make sure you get used to it or you write it down. So modulus of elasticity, elastic modulus, or Young's modulus. It's the person's name. Young. It seemed he was very young, not old. So Young's modulus. Elastic modulus. So yes, another one.
Another is a modulus of rigidity.
Very good. The letter for it. Lazar, yes.
G.
G. You work together. Lazar, Josiah point, and then you. I do remember your phrase, but you're not your name.
Evan Mushler.
Evan Mush.
Should be the first name.
The first name. I point to you. So G modulus of rigidity or shear modulus is something that we go over today also. So shear modulus is another name for it, or simply shear stiffness. So all of these the same basic quantity. All right. So now with those review, let's go over torsion. Guys, I will not share my notes. Instead, you're welcome to take pictures as needed. So these are all given in the textbook, but I compile them into this list. I want to make sure that everybody is here present, really puts the time, and then write these down. Take pictures, and then you have them. Is this? Let me see. It will be. I updated my, yeah, let me open this up with. I updated my tablet just yesterday and I messed up a lot of things. So let me open up with Edge and see what's much better. All right, I'll give you time. Whatever you want to do, if you want to write or take pictures, and then we'll go over this. We go over the equations. Again, this is really the entire equations that we need from chapter 3, all given to you in one slide. And then I'll go over some examples, and then we get back to this slide over and over to really make sure that we covered everything. And meanwhile, let me remember names. Evan, yes, I remember you. And Francisco, where are you? Francisco, right? AJ Kennedy is up there. Tyler Destrucker, remember you, yes. If I can read it, is it Gray? Gray, yes, all right. Audrey, all right. Is it Leah?
It's Leah, yeah.
Leah, okay, very good. Sander, very good. Johnson, very good. Jack, how would you pronounce your family name? Family name. Pronounce it. Yeah, it's hard for me to pronounce it. So I will simply call you with your first name then. Nathan, is it Schaffner? I'm not
Yeah,
sure.
Schaffner.
Schaffner. Ethan Jackson, very good. Reagan, I saw you. Gabe Twist, yes. Cole Aiden.
Arden.
Arden.
Yeah.
Thank you, Cole. I do remember you as well. Josiah, I do not remember you anymore. Drew Lainama, yes. Lainama. Mohammed Wasi is, yes, Mohammed, right?
Yeah.
Nathan Smith. Nathan. Braden, yes, there. Is it Justin? Yes. The second to last letter is E, just 10. Okay. Jacob Dozama, yes, there. Pronunciation, I know you, but. Koro and Kiro.
Hero.
Kiro. You're tricking me?
Well, it's, Hero is a nickname and then Corollas as the full name.
Oh, I see.
Yeah.
When they come together, you pronounce as cool. Okay, I see. I see. All right. Aidan O'Neill. Okay, Aidan. Stardy. And Dylan. Nicholas. Jesus. All right, very good. All right, so speaking of torsion, now you guys gave me some applications. In practice, where would you think torsion is happening? Yes, Jacob.
In cars.
Yeah, but be specific.
Oh,
Then I was a fish car. Yes, Jacob.
like in the axles.
In axles. I'm not sure about the order, but maybe future class I'll go one at a time so that I'll keep the order. Yes, again.
In the suspension.
Suspension twist,
Yeah. Rotating suspension.
if they rotate.
Yeah.
If you're talking about bending, then that's a different thing.
There's a torsion bar suspension. It's a fixed suspension. GM uses on their trucks and old Chrysler products uses. Specifically, it'll basically, you take a spring, then you uncoil it, and then you shoot it out back towards the back end of the car, and then you would use it.
Yeah, you're showing that. That is the case. You're showing that. Because sometimes it's just holding things there. That's different. Or if you think that it's bending like this and that is viewed as torsion, it's not. But the way that you explain that that is torsion. So gave the point? Yes, please.
Your drive shaft?
Drive shaft. Help me with name again.
Great.
Great. Great, yes. Point to you. Yes, please.
Like manual transmission?
Yes, very good, yes. So many gears there. And was it Nathan?
Ethan.
Ethan. Ethan Jackson. All right. Anything else? Yes.
An end mill?
Emily, yes. Remind me, again, I need about a week to remember our names.
Oh, braid. Our shackle?
Okay, yes. Anything else? Look at smaller dimensions, Jacob.
A lathe.
Yes, because you got to a point that we move on, yes. Leo?
I say a key and a lock.
Yes, exactly, yes. I was looking for that. Is it Sobic or Sobic?
So,
Sobic,
yeah.
okay. Yes.
Your ignition switch?
What switch?
Ignition?
Yes. Especially when you get to the end, not early on that freely moves, right? You already got your point. Anybody else? Yes.
A screwdriver.
Screwdriver. Did you get the point on this or not?
No.
No, okay. Drew the point. Anything else? Yes.
Drill
Drill bit. I was looking for that also. Remind your name, please.
Nathan Smith.
Nathan Smith. Yes. Anything else? Yes.
It's unrelated, but can you go into full screen just so?
It is full screen. It is.
There's
The three dots and it says full screen.
If you hit F11, the top bar will go away.
Oh, you mean, oh, I see what you're saying. I'm sorry, I see now what you're saying. All right, then let's see if, then the question is on Microsoft Edge, how can do that?
Should just be F11.
If you can type.
If you got it on the keyboard.
Then you make me take advantage of technology. You said control what?
F11.
Oh, F11. Yes, point to you, Jacob. I wonder how you remember it. Yes, there was AJ,
Are like screws and like bolts under?
was mentioned, yes.
Oh, it was mentioned, okay,
Yes.
I'm sorry.
No worries. I don't know how much it helped. Maybe I can zoom it. Man. Is it better, Nathan?
a little bit.
Okay. There's free space here if you wanted to move. All right, so given all those applications that you said, then these equations apply with one caveat that I'll touch on later. All right, then suppose this is one of the applications that you mentioned. Doorknob, by the way, is another one. So we apply torque, so T goes for torque. All right, T goes for torque. We torque this shaft. So the reason that you see opposite, equal and opposite torques, that means one is reaction to the other one. So basically means that's fixed on this side. Or the textbook decided to show that as open, but put opposite torque. These are the same thing. All right, we're torquing this object, and we're looking at this cross section in here. So it says that the torque basically distributes between the points on the cross section. If you look at this middle line as the center line, and then if we measure R away from the center line, that's the radius that you see this equation. The further away the point from this center line, the more the R. Therefore, the more the torque that, or the more the weight that it takes from that torque. So, if it's really on this center line, there's no distance away from it, no torque will be applied to that center line. As you get away from it, the more torque it develops in that point. So really, you visualize that cross-section as a combination of layers on top of each other. That's the cross-section. So what this torque does is these layers slide over each other. So whenever slippage occurs, then you talk about shear stress. Like two surfaces on top of each other, and then you glue them, you pull or push on one, and then slides, and then we have shear stress V over A that we went over. All right, so that's why in this case we only go over shear stress due to torsion. That's the equation. Tau still is used for this case, but we qualified with saying it's due to torsion. The equation is tau equals TR over J. T and R, we went over those, but J is a new parameter, perhaps the first time you got exposed to it. It's a big name, please write it down, long name. Second, polar moment of inertia. Second, polar moment of inertia. Second, polar moment of inertia. That's, in general, in this integral equation, but we're not going to do any integration. Instead, we're going to look at two geometries for which J would be given closed form. For the solid circular geometry, like this, or hollow, basically tubular geometry. Pi halves R outer to the fourth. For this, there's nothing, no cavity inside. But when there is cavity, you subtract the J of the outer minus the J of cavity. So that's why minus R inner to the fourth is included. The unit of J by inspection is meter to the fourth. You may not have seen any unit like this. Meter to the fourth. So I will ask yourself this question. Does this parameter have a physical or geometrical meaning? It turns out yes. J, it might be part of the test. J is a measure of resistance to torsion. mass, force equals ma, Newton's second law, is a measure of resistance to acceleration. So this is a measure of resistance to torsion. The more this value, the bigger the value, the bigger it resists to torsion. All right, it turns out, because of this equation, when r equals 0, when we are right at the center, is no tau, so tau is 0. As we go further away, right on the outer surface, we have maximum shear stress. When there's cavity, yes, the cavity is hollow, so the shear stress, instead of starting from 0, starts from non-zero stress. Still much smaller than tau max. So that means, if, let's say, you are working on mini Baja or SAE car, when tubes are involved, when the case is just load, the load is just torsion or torques, then it makes sense to use tubes rather than solid pipes, because we see that there's not really much going on, there's not much going on the inside. Why not making it lightweight? Take advantage of basically material. Still not losing any advantage there. So what we want to do, because then this shear stress depends linearly on R, we see that behavior is linear from 0 going to here, from tau min to tau max on a line, then we can write this equation. Tau min over tau max, they are proportional to the radii of the two. So what we want to do, let's do some examples and then get back to this to really learn more. First example. That's where we need your calculators. Pull them up. So toward the middle of the class, if I forgot, just please remind me. So 11, let's say 20, we'll get 10 minutes break. So we did not learn everything yet for this example, but let's do the first two. Minimum and maximum shear stresses. I'll give you time to write down the statement. Certain parameters like geometrical or material properties given, the load is given. So first we want to calculate minimum and maximum shear stresses. So raise your hand please. What is the equation for shear stress? The load, we see that is torque. So shear stress equation please for torsion. Yes please.
Tau equals V over A.
Is it torsion? Just look at the torque. So it's not that bad.
Okay.
Yes. Correlates.
Tau is equal to torque times radius over second polar moment.
For J.
That's it.
So that means that we need J calculated already, right? Because we need it for both, so let's calculate that first. So let's point to you, somebody else, give me the equation for J for this particular case. It's solid geometry. Look at the cross section, Jacob, please.
Is it J equals integral R squared
We
dA?
just went over that, we're
Oh,
not doing
sorry.
any integration, right? So give me the crossover. Can I look that up? You have it, or you want me to go back to
That
it?
would be 5.
Give me the first equation for J, for this case. Integral is the general form.
Yeah.
We're not gonna do any integration, right? We're gonna do, yeah, give him time, please, Jacob. One more chance, Jacob.
With the 1/2 pi.
Yes,
R.
that's the
That's
one. Continue.
1/2 pi R/4.
Very good. Yes, guys, please bear with everybody. We're one big team. Somebody that needs more time, just give him time. Yes, that's solid geometry, or out there to the fourth. So, guys, I want you, I don't know whether Professor Kormova had went over that or not. Put this table that we're gonna compute today together in your equation sheet. Jacob goes on before I forget to point to you. So, in this course, or many other higher level courses, in fact in engineering, we tend to deal with numbers that are on the two extreme sides, whether really big or really small. That's the nature of engineering. So to be able to communicate them easily, engineers came up with these intensifiers, like millionaires. They never talk in cents, right, or dollars, they talk in millions for simplicity. We do the same thing. So let's put these. So this list is no way exhaustive. If I remember correctly, these are the main ones that we use. So, and so this is nano, this is micro, this is milli, this is centi, kilo, mega, this is giga. So the value of this 10 to 9, negative 9, 10 to negative 6, 10 to negative 3, 10 to negative 2, 10 to 3, 10 to 6, 10 to 9. So if the value is really small, we never say 0.000001. Instead, we use these intensifiers. If you are used to that way, which is absolutely fine, let's say for high school problems, but engineering that would not work. Because if you put small value like that in your calculator, depending on the precision of your calculator, you may not be given the correct value. So instead, you have to resort to this approach, scientific notation. So let's get used to that from this point on and take advantage of it for subsequent courses. So kilometer is 1,000 meters for this reason, 10 to 3 meters. 1 cent is hundreds of dollars, 10 to negative $2. It's the same thing. People, let's say in YouTube, in different software, they have certain followers, certain number of followers. They say we have 1 million followers, or 1 kilo, 1K follower. It's really, it goes with this. So, with that said, what we do, outer radius, we see that diameter is given as 10, so radius is 5. Centi is 10 to negative 2. I suggest you do always this way. You will not miss anything if you do it this way. Do not put 0.05, because you're going to have smaller numbers, and that will not work. So adopt one approach. Always do scientific notation like this. And do the easiest reading. So J like this. The first two people, please give me this value that you found, and we know the unit will be meter to the fourth. Give me this value, I'll give you a point. First come, first served. Yes, Josiah one, and then hold on for the second one.
9.82.
No, hold on for the second one.
Oh, okay.
Yes, Wasi, you said you wanted to be called Wasi. All right, go for it now.
I got 9.82 times 10 to the negative 6.
Can you give me two more digits? Give me 3 digits. From this
9.817
817 to 10 to
the negative 6.
86. And then Wasi, are you confirming or giving different value?
It's the same.
The same. That's correct, a point to each. All right, 9.817, 10 to negative 6. All right, we have that value. Now we can move forward. We're calculating tau min and tau max. So we said the equation is TR over J. Then we are after min shear stress, then radius has to be minimum. Everything else remains the same. So torque T is given. We know that the unit in SI is Newton meter. That K then is intensified. Converted to SI by putting 10 to 3 there. R min is really, it starts from here, so really 0. So really it's 0. Not bother with calculating. But a solid shaft, minimum radius is right in the center, that's 0. Then we care about outer. That means if you want to analyze shafts, just always just look at the outer surface. If the outer surface is good, everything else is good. So that simplifies things. For the maximum, we know that the outer radius is 5 centimeters, and J is the one that we already found. All right, first 3 people, I want tau max in megapascal. Whatever you find from your calculator, you have to convert it to mega. That means you have to divide by mega to get in mega. We know that mega is 10 to 6. 1 over this. Two more. Wasi is 2.
Bless you.
Josiah, yes, Josiah. All right, let's go for it.
254.660 millimeters.
Very good. Are you confirming?
Yes, I got the same thing.
The third one was Wasi confirming. All right. That is correct. This is about honesty now. And you're doing this for your sake. All right, Josiah, Cordes, Wasi. All right, we learned this much already. We were able to comment on that. Yes, Josiah.
I got 254.66. I noticed you put 0.65.
Right, it really depends on how much we do here,
Okay.
right? Yeah, so it's round of error, and the last digit doesn't matter.
Okay.
So some people calculate J, put this thing in here, it would be most accurate. But really when we say megapascal, the decimal digit does not count much.
Okay.
All right, so we said the objective of the course is to be able to comment on the mechanical safety of this object. Under this torque, is this safe? Then the question is this, what material is made of? Yes, we know about G, but G is not about strength of the material. So if I give you some property in terms of strength of the material, then you'd be able to comment on it. So that property, if you learned it, if Professor Movahed already went over that, then you give that parameter, the subscript U goes for ultimate. That means the cap value that the material can safely take. So simply, the ultimate value is called, in this case, shear strength. All right, suppose we're doing extra work here. Suppose this is given as 300 megapascal. Now the question is this, answer me, raise your hand. Is the material safe based on this value? Raise, I saw you nod at it. So it would be fair to give her, right? Leo, and I saw your hand almost at the same time. What do you want to say? Yes. Yes, based on this, the reasoning, because this is greater than how max that we calculated, then we would say it's safe. As easy as that. You should not elaborate any further. If I ask something like this in the test, you will calculate how max, and you compare with the max value that you're given. So Jacob and then Leo get each point. Yes, next time you raise your hand so that it be fair to everybody. All right, we learned this much and then we did it. We have about 5 minutes. We can do a little bit more and then take the break. But before that, guys, any questions? Yes.
Is the minimum radius always 0, or when does that change?
Yeah. So if you look at this, if it's hollow here, then the minimum radius would be this.
Oh.
Yeah.
Right.
We're gonna have another example like that next for the next one. All right. So now we want to go over this parameter, the angle of twist. So let's get back to it. First of all, I have to give you a disclaimer. These equations are valid only when we have these two geometries. If not, these equations do not apply. First of all, the question is, what do you do there? Anything comes to your mind? Let's say in caulk, you're working on a shaft that is not circular or tubular. What do you do? If these equations do not apply, then you should look at finite elements. That's another course that you take. It's more computational. It looks at every geometry, but with a lot of computation. Then you have to resort to simulation software. But for something like this is an introductory course. We're able to calculate. So why is that? The reason is this. If you look at a circular geometry, when you torque it, circles remain circles. But for a rectangular geometry like this, it distorts much. That really it makes it really hard for these equations to remain true. So this is called warping. So because of warping, these equations are not valid. All right, so that's the disclaimer. Now, the next parameter that we want to learn, the textbook calls it this big, angle of twist. Simply, we're talking about angular deformation or deflection. The letter, the Greek letter, phi, or some people pronounce it as pi. I'm not Greek, so I don't know which one is correct. So let's go with either one. And the next one is shear strain, the Greek letter, gamma. In this course, we have so many Greek letters. So the two equations are given. For phi, TL over JG, T and L We went over those. J is still the same as above, second polar moment of area. And G is the shear modulus that we went over. Shear stiffness or modulus of rigidity. All of them work. Keep in mind that in this equation, phi should be evaluated in radians. So this is also in radians. Yes, you could convert it in degrees. Degrees could be given to you, but if you want to use that in the equations, you have to convert it to radians. So the shear modulus, we said it has a correspondent for normal stress, in normal stress case, and we said it's uppercase E, elastic modulus. So in practice, how do we measure those? So we use load frames. So if I pull up this in chapter 2, so load frame is something like this. So we put the object right in here. Adobe does not work well on the tablet today, but we put specimen like this or a dog bone shape like this. We put it in here, and then this is the computer with this, and then the hydraulic jacks. We exert load to that. We normally, with this machine, we normally do up and down, basically either tensile or compressive loading. And for something like this, it costs around easily 100K. Unfortunately, in ME, we do not have this machine, even though this was my topic of research, but because we did not have it, I had to really switch to a new topic. And for machines that do biaxial loading, basically both up and down, basically on the surface, it gets easily above $500,000. So load frame, something like this. For torsion, let's get back to here, something like this. One of my students in co-op was working on a big shaft, and the machine that they had there was really huge, really huge. So the load comes from here, suppose the load is here, and then this is the object that you have. You have data acquisition here, you calibrate it basically, you load, and then you record it. This is the object. That's how you calculate G. All right, so with these equations, all right, there's one more thing before I forget, before we get to examples. So ductile, or ductile, some people pronounce it, versus brittle. Anybody remembers what those mean from chapters 1 and 2? Gabe, please.
Brittle means it's really hard and it doesn't have much flex to it. And so if you put force on it, it'll stay mostly rigid until it just breaks. For a ductile, it'll just kind of like flex and stretch because it's soft.
Very good. So yes, Gabe, so the point is flexibility. So metals are mostly ductile. So what that means is, as Gabe said, when you load them, they do not easily break. They take the load, they try to deal with it, they neck if you pull on them until they break. But for brittle materials, like what we have here, bricks and blocks that we have here, they're good in compression, but not in tension. When you put them under compression, they take the load substantially until they abruptly fail. So that's the main feature. So they're really good in compression. So that's why in buildings, because they have to really take all the load from let's say what is on top of them, So they're really good load-bearing pieces. They're mostly in compression. That's why you see them mostly in buildings. But for any reason, you think that the wind from the side could be significant, that it causes them to bend, therefore they get some elongation. We're going to go over that in chapter 4. Then you see that they're not good. So that they're not good in tension. So that's why you see them, they're strengthened with rebars. So that's the idea. They're not good in tension. We add them a metallic component to make them also good in that scenario. So how can we distinguish one from the other? So in tension, we said if you pull on them, they exhibit necking. If they necked, then we know that they're ductile. If not, if it's clean cut, then we say it's brittle. What if we torque them? So the torque, again, is not something that we impose to the material. It's what we see in the material. And we try to report to you. So if you torque a ductile material, it's clean cut, as you see here. It could be part of the test, a quick, let's say, multiple choice problem. In contrast, if you torque a brittle material like this, they may cut at about 45 degrees, either to the right or to the left. About 45 degrees. For instance, next time when you wanted to eat a cucumber, try to torque it. You know that's brittle, and you see how it cuts. About 45 degrees. So that's one way of distinguishing these two materials from each other. All right, I see you're done with this. So let's now continue with that. Actually, let's get a break and then let's come back to finish it. Please come back. I have three clocks here. Let's go with this. All right, I don't see that here now. What's the time now?
11:45.
Let's come back please by 11:55 in 10 minutes. You said 45?
25.
25, 35. Okay, that's why you were surprised. So we want to continue with this example, calculate angle of twist, which we simply call angular deformation or deflection. So we said the parameter is phi for that. TL over JG. So T as before is given 50 kilo. So I'll convert it to kilo by 10. Convert it to SI by putting kilo there, 10 to 3. So that again, as a reminder, it makes sense that you put this in your equation sheet so that you always have it available. How would you look at it? As you use this in your examples, you tend to memorize it. Length is 1.5 is given. J is the one that you calculated. And G is 120, 10 to gigas, 10 to 9. Remember that. It gives you the value in radians. I want the first 3 to give me that in degrees instead. Calculate it in radians, but convert it to degrees. Give me that in degrees. The first session, let's go for the first 5. First 5. As you haven't raised your hand, so that I record you as one person. And doing this in class, you resolve all those issues with your calculator. Many of students from the first class showed up, they did not know how to do storage capability, take advantage of it in their calculator, because we had long equation toward the end of the class. We learned that. Gabe is one. And then one just found that the calculator did not do the way that he thought it would do. Wasi is 2. Your name, please?
Justin.
Justin is 3. Audrey, that's 4. One more. Five. All right, Gabe, go for it. What was the number you found? In degrees, please.
Degrees. 63.665 10.
Degrees, right? What you find from the calculator is radians.
Oh.
If you did not do that, there's another person after 5 to 6 person. Anybody else? If you do that quickly, you get that back. All right, Nate, let me see, I think I know your name, Ethan, right?
Yeah.
All right, then the second person was who? Was it, yeah, was he, what did you find?
I think, I got 10.9 degrees.
Yeah, that's off. Then we need one more. No, you guys already raised your hand. Gabe, and then, oh, no, you guys are in. I want to give a chance to another person. Gabe is 6. Okay, Gabe, go for it. That's off. Guys, this is simple calculation. When you want to convert from radians to degrees, what do? You do 100, you multiply 180 by pi. So radians, divide by radians so that you cancel it out. All right, then you will be next. What's your name? What's your name?
Evan,
Evan, let me see where you are.
at the top,
At the top. Yes, Evan Mushler. So what did you find?
3.647.
All right. Out of those people, who agrees? Actually, whomever agrees, really honestly, raise your hand and keep it up until I pronounce your name, then I give you a point. All right, Evan, put it down. Remind me your name. Aiden O'Neill,
Yeah.
point. Jacob Dozama. I forgot, say it again.
Justin.
Justin, should we post it, right? Yes. Manon, you said?
Manner. Manner. MANNER.
Oh,
My handwriting might be bad.
yeah, I gave you a point. Is it, I don't know. Johnson?
Nathan Chopper.
Oh, looking at that, and then with that, oh. Yes, Nathan, point to, I know Drew, okay, down, Gabe, Chris, Tyler, that's Chuck, AJ, Francisco, all right, good. Leo and Audrey. Remind me, please. Gray, yes. Heck, Nat, is that?
Yeah, yeah, what's that?
All right, yes, if from your calculator you would get in 2 decimal digits, something like this, it would be radians, it would be 3.44 degrees. So last is asking for maximum shear strain. So we learned gamma equals R3 over L. So if you're going for max, then R should be max. So R max is outer radius, which is 5 centimeters. Phi is the one that we just found, but make sure that even though we are calculating a different unit, the one in the equation that we need is the one in radius. So put that one in. The length is 1.5. So this is unitless. So something like this, but you may see something like this in the textbook. So the textbook converts it to micro, but because it's unitless, it's by itself, it's pronounced as micron, rather than micro nothing. Micron. So when it's an intensifier, when you say micrometer, by a unit, you pronounce it as micro, when it's by itself, you pronounce it as micron. That means 2,000 times 10 to the negative 6. It makes it easier to communicate to other people. So with one example, you were able to calculate or showcase applicability of all these equations. Little by little, we want to make it more elaborate and more practical. But before that, any questions? Yes, I see some people are taking pictures. It's a good time to take picture of the note. You have everything set in that slide. That's why you're not losing anything. Done. Let's move on to the next example. Audrey, you were asking a tubular geometry, and that's the one. So not only the geometry is changing, I'm also changing the description of the problem so that we look at a more practical problem. Guys, let me emphasize. At any point you thought that something is unclear, need more explanation, just please ask me. I'm doing my best so that you learn everything just in class. Remember that we're engineers. Not only we should be able to tackle long equation calculations, we should also be able to come up with that equation first of all. We should be good analyzers. So in practice, customers come to you, they say, I want this design, I want something that does this, and this. Then you should be able to come up with that design. If your design satisfies all but just one, still not a good design. Customer will not be happy. So we want to practice it as part of this class. What changed from the first to the second example is this. Geometry changed, it's hollow now. All right, math changed a little bit, but the description changed. First it says, find how much load you can apply to this, as opposed to knowing the torque. So how much this material, this object can take if two conditions, material property, given to be this, and then given this condition. So there are two conditions. And we know that each one gives a limit to the value of the torque. So each one gives us one value of the torque. Then out of the two, we have to find the right one. So that's the procedure for this. Then, once we figure out the conditions or criteria, which are these two, then literally write down the equations for the two. And then solve them for the unknown, one at a time. But because J is needed for the two, let's calculate it early on. Because this is hollow this time, we know that pi halves are outer to the fourth, are inner to the fourth. So I create the structure first. I put the outer and then inner. Outer, as before, is 5 centimeters. And inner. Open question, raise your hand. Give me the inner radius, please. I'm not sure who was the first, but might be, yes, AJ, please.
1 centimeter.
Then, Josiah, you have an option, 1 centimeter. Okay,
The inner radius would be the empty part, right?
I don't know, you answered that, you asked me.
4.
4, believe in yourself. Inner radius, right? Measure from here, that's the inner, and that's the outer. Yes, indeed 4. With that, does that make sense now? All right. So 4 centimeters. So we go with really this definition here. This is the inner, and this is the outer.
Can I see that?
Diagram.
No, sorry, the one in the problem. I won't-
The problem that was going there, here.
Okay.
All right, so if you
I thought,
calculate
yeah.
this,
I thought T was measuring from the center to the.
I see,
Yeah.
but the thickness was given.
Yeah.
But let me give the point you gave.
Do I get bonus points for believing in myself?
You were not believing yourself, you said, we're doing like this. Then for that, I should give you a negative point.
You don't need that. I'll take the one.
I gave you one. All right, the first three, please give me this value. One, two, one more. Game. All right, please go for it.
I got 5.79 times 10 to the negative 6.
Very good. So listen, for internal calculations, it suggests you go for 4 decimal digits so that in the end you have around 2 decimal digits correct. You see, everything in the end depends on the intermediate calculations, right? In practice, it turns out to be this. If you go for 4 decimal digits for intermediate calculations, the last one will be good for up to 2 decimal digits because of the non-linearity of the procedure. All right? So, and then, Jesus, do you confirm that value or not?
Yeah.
And then Gabe. All right. Remind me again.
Justin.
Justin. Yes, I see that. All right, Jesus and Gabe. All right, yes, that's 5. I'll go for one more decimal digits. All right, that's J. So we said the first condition, tau u. If you want to really solve for the maximum torque, that means you're pushing the material to its limits. Only then you really can calculate the maximum torque. That means you have to equate the strength value with the maximum shear. For the first condition, and for the second one, tau u with tau max. That's how you calculate the max values, the extreme values. You're pushing the material to that condition's limit. So tau u is literally given as 120, but remember, mega is 10 to 6. Always convert it to SI, and you'll be correct. On the right side, tau max now depends on the torque. That's an equation. We learned that that's TR over J through the first example. And then T really is tau T max, R over J. So let me improve the writing. T max R over J. And we know that tau max is also occurring at the maximum radius, the outer surface. All right, T max, we do not know that. Leave it as unknown. R max is the outer radius, which we know to be 5 centimeters, and J is the one that we found. So this gives us T max value based on this criteria. And I want you guys, the first 5 people, give me this in kilonewton meter. That means divide the number by kilo. What will you get from your calculator? The first 5 people. Raise your hand so that I count you as 1. It's good that you guys are discussing that. If I can help, just also include me. First 5 people, these are bonuses. Take advantage of it. Guess Justin 1. Wasi 2. Leon said 3. Four, Taylor. Very good. 5. So we have 5. Yeah, what did you get for this? Yes.
Oh, I got 13.91.
Those other 4, agree or not? What did you get? You disagree.
I got 1.59 times 10 to the negative 7.
What did you get?
I got 0.6955.
All right. What did you get?
I got the same thing.
But who was the 5th one? Yes, Taylor, what did you get? Okay, both you get a point. I need 2 more. Calculated, it's about honesty. Calculated, and it has to be 13.91. So well done, Leon. I would say Leon's team. Leon, where are you? All right, your point was senior point, and Taylor. 2 more. Calculated is about honesty. Gate confirming it, right?
No, I got 1.03.
So may I have your attention then? How we calculate this is as follows. And this pattern, which is really 2 ratios are equal, occur a lot in this course. Yes, there are different ways in solving this, but you may need to take advantage of the portion that you do because it happens to be the fastest, in my opinion. So suppose I want to solve for C. How do I do that quickly? I simply say this: C equals ratio of 2 things. Multiply the 2 that are off diagonal to C. So off diagonal to C. This is one diagonal, this is another one. So if you want to calculate for C, calculate A and D in the numerator, and whatever remains on the same diagonal as C, which is B, within the denominator, that will be C. Therefore, this T max would be, if I put 1 in here, what is on the same diagonal, on the off diagonal to T would be these two. That means multiply these two in the numerator. Whatever remains on the same diagonal as T max, which would be 5 times 10 to the negative 2. It gives you that value. Now, this formula works whether you go for D, B, or A, doesn't matter. Suppose I want to solve for D, whatever is off diagonal to D would be D and C. Divide by whatever remains on the same diagonal as D, would be A. But it works all the time. You just need to get used to it. So, yes, Josiah confirming it, right?
I have 13.
All right, very good. Point to you. Again, this pattern shows up over and over. Get used to it, and then you easily and correctly calculate it. One more. Almost, did you calculate or what?
Yeah, I also got the same.
Almost at the same time, I divide the point between you guys. Each one gets a negative point. Did you get that?
I just have a
And
question.
what's your name?
Braden,
Braden, remind me.
Arshaw.
Yes, I saw that. Audrey, I was joking, each one a point. Yes, what's the question?
When, before you convert it to, kilo.
Kilo, it should be 13,000 something.
Yeah,
right?
yeah. What is that in Newton?
Newton meter.
Newton, it's okay.
Yes. Just you see, I put the unit here. Braden, I put the unit here. Get rid of adjective, steps.
I just wanted to know what it was before I converted it to.
Yeah, I put it here.
Yeah.
Just get rid of K, that's the unit. All right, so now let's do the second one. So it's given as 1 degree, that's the ultimate value that we're interested in, or the customer is interested in. 1 degree, but remember that we have to convert it to radians for that to work in that equation. For radians, if it's in degrees, that means you have to put 180 degrees in the denominator so that the two cancel out. Put pi in the numerator. So that's the max value given. And the right side is the equation, TL over JG, and T is the T max. We do not know that. Based on this criterion, we want to calculate it. So it's a new value. It could be the previous value, but we have to calculate it. So leave it as an unknown. Length is given as 1.5. J is the one we found. And G, as before, 120, 10 to 9. So this one gives us a new value for T max based on this criteria. 5 people for this. Do the same procedure. Off diagonal elements to T max. Multiply them, divide by whatever remain on the same diagonal as T max. It gives you T max quickly.
Bless you. Yep. 120 times 10, 9, T max.
One. Two. Three.
Is it supposed to be in kilonewtons as well?
Yes, I put the unit there. 4. And Leo, 5. All right, Josiah, go for it.
I got 8.093.
The other 4, are you agreeing or not? What did you get?
I was supposed
Yes, what did you get?
to, 7.88.
7.8. Which one? You have which one?
8.093.
So you're going for A. Justin and Jacob, which one?
I got 8.344.
8 point something. And you-
I got the same.
And then fifth one, okay, we already have 5. So 8.09 was correct. So, so what did we do? We said T-max, right? With our approach, we said that whatever is on the off diagonal element. So just look at this. This is on the same diagonal, and this is off diagonal element, right? Do you see how I'm doing this? So on the off diagonal element of T-max are these elements. So 1, pi, and this number, all of these numbers go to the numerator. What will remain on the same diagonal as T-max should go to the denominator. 180 is one, and 1.5 is the other one. That gives you this. All right, so redo this. I need one more, but the first four get their point. So Jacob, Justin, Josiah, 3, and then there was a fourth one here, I forgot. Neon, yes. Yes, I gave you.
Yeah, I just had a question. What are the units for the final number? Is it new meters?
Because you can vary the kilo, yes, I put the unit here.
Oh, it's kilonewton meters?
Yes.
Okay.
Once you divide by kilo, that means it's kilo.
Okay.
The unit for torque is always Newton meter in SI. Yes, you can vary.
What was the answer?
What did you get?
Oh, 8.09?
Yes, that's right. I'll give you a point. Remind me your name?
Arshambo?
Yes, I saw. Great, okay. All right, so now I'm repeating the first example. It says, also determine the corresponding minimum and maximum shear stresses. All right, actually we're not done. So we have two torque values. If I apply the first one, then the material will almost fade. If I apply this one, then the second condition will be at the verge of failure. Which one is the max value that you should apply? Raise your hand if you want to answer. Yes. Or less. Well done. So really, team, if I call this comma 1, comma 2, so in fact, we have a sort of a paradox in this course. We are after max, but we are really picking the smaller one. I put an exclamation, because if you go for the bigger of the two, then the first one would of course break first. So you cannot go for that. So really for that reason, we go for the minimum of the two. So that is the value from this point on. So now with this, I want to calculate the minimum and maximum shear stresses. So tau min would be TR min over J. So tau we just found it 8.09, 10 to 3. Inner radius we found it to be 4.4 times 10 to the 2. J, the one we already found. So tau min gives us 55.83 megapascal. For tau max, we can do the same thing, TR max over J, but I want to do it this way. Tau max, so that we show the applicability of this example that we learned, this equation we learned right here. The two are linearly dependent on radii. So I use this tau max will be R outer or inner tau min. R outer is 5 centimeter. I can leave it as centimeters because they do cancel out. 5 over 4 And how many I can leave it in mega, and the result will be in mega. So read this test, 69.79 megapascal. So that means this object at max can take this amount of shear stress. Think about it. We said the maximum that the material can take is 120 megapascal. But because of this extra condition, you cannot apply the stress more than this, because the second condition will be failed or surpassed. Yes.
So the units for the 5 and 4 don't matter to the cancel.
Because they cancel out, I did not convert it to meters, yes. Yeah, logical thinking, critical thinking is a big thing with engineering. Corliss, before I forget, let me give you a point. Yes, it's a good time to take a picture. We're done with this example. Apple or Samsung, I think they have to give me something, right? I'm showcasing their products here. I have to take a lot of pictures. All right, guys, any question on this example? All right, I'll be posting your homework soon, and I'll make the due date, let's say Sunday at midnight. All right? So I put the policy for homeworks on Blackboard soon. When I post that, I'll get back to you. There are some limitations that Blackboard has, unfortunately. Even though I contacted them and asked for help, the software did not really allow those changes to be implemented. So I had to come up with a workaround. So the idea is this. I want to give you 5 attempts for every homework. So to be able to do that, I cannot give you all 5 problems in one set. I have to give them separately so that you have 5 attempts for each one. All right, so that's the workaround. So I put the policy in Blackboard, so it will be due on Sunday at midnight. So make sure you do that on time. For any of the attempts, you get it correct, you got that correct. You don't have to continue for the subsequent attempts. Let me see what else I want to say. Take advantage of my office hours early. If you shoot me email on weekends, I cannot answer that. Be mindful of it. Thursdays, 11 to 1. That's for homework. What's your question?
I had a question with the last problem. I was confused with how you got 4 for the inner radius.
Yeah, just look here. The thickness is 1 centimeter.
Okay.
This is 1, so this is the meat of it.
Okay.
This entire thing is 10 centimeters. Half of it is, the thickness here is 1. So what is this?
3.
Oh, okay. So
That's
it's
the
5
inner
minus-
radius.
You take 5 minus 1 inner radius. Okay. Thank you.
Wouldn't you do it that way?
Thanks.
All right. So for homework, something like this will show up. Of course, the numbers change. For each attempt of the same problem, you'll have the same statement, but the numbers change. That means you can take advantage of the value that I give you for each attempt. So you can correct yourself as needed. But for the next attempt, the numbers change. So take advantage of the earlier attempts if you have to. So This shaft is in line with those examples that you had given me. It's a telescopic or composite shaft, but we have two geometries there. But remind me, class ends at 11:20, right?
Yeah.
All right, so we're interested in angular deformation of this point, A, given the two segments. So if I say that phi of this is AB alone and phi of this is BC, you can reason that the total is really, at this point, is the summation of the two, or superposition of the two. And phi, I know that the equation is TL over J, G, and I factor out G outside, because it's common material. So that way you make the calculation easier. And I give the subscripts. This is for AB, this is for C. The catch for this and the one that shows up in homework is really just the two torque values. So bear with me, let's put in the other values that we already know. And then we figure those torque values in the end. So length AB by inspection is given as 0.4 meters, and length CD 0.8 meters. In fact, this is a reduced version of the example given in the textbook. Again, textbook for some reason is interested in mathematical complication without changing the engineering aspect of it. It puts some cavity here and then another node there, just mathematical complexity. And we're not interested in that. We still retain the crux of or conceptual aspect of it with even reduced work. All right, JAB, for both, you see that they're solid geometries, so pi halves are AB to the fourth, pi halves are CD to the fourth, apply. So let's plug in values. In tasks, always make sure you show me the work. I'll put it like this, so that in case there's any miscalculation, I can give you the majority of the points. But if you do not show me the work, then it's hard to really decide. Work will be really graded. All right, J. So radius AB by inspection, diameter is given. So 30 becomes 50 for radius. Milli, we learned that is 10 to the negative 3. The next component, 60, becomes 30 for radius. Milli is 10 to the negative 3. And G is 77, shear modulus. Giga, as before, is 10 to 9. We have about 4 minutes. We have about 3 minutes now. Can you give me your attention so that for your homework you have plenty of time to work on it? So I'm going to come up with the torques. They're not literally these two values, but they are in terms of these two. So how do we determine those? Just look here. Yes, of course, free body diagram approach that we learned in statics applies. But we are advanced now. We can calculate them much more easily. So pay attention, please. So I want to come up with TAB in this region and TCD in this region. For TAB, I say like this. Assume that TB is not applied at all. Would you agree that TA affects both segments? If I apply only TA, would you agree that it applies, it deforms both segments? All right, then TAB at least has TA in it. And TCD has TA in it too, because TA affects it. But now assume TA is not there, only TB is applied. If I apply TB, does that distort AB at all? No. So then it does not play any role in here. I should only apply to TCD. But now, because TA and TB are applied in the reverse directions, I have to subtract them. So assume this direction is positive, then I have to do TB again. Again, let's analyze it. TAB. In this segment, only TA deformed this segment. What happens to B only gets affected by TB. So past TB, TB applies. Past TA, only TA applies. So past TA, TA applies to both, but TB applies only to past B, which would be in this segment. So that's why TAB is TA, TCD is TA minus TB. In homework, the only thing that changes is that the two are in the same direction. So instead of minus, you should have positive there. That's the only thing. So for AB, that's 1 kilo, that's 10 to 3. This is 1 minus 2, 10 times 10 to 3. We have 1 minute left. If we had more time, I would have given you the chance to calculate it. But let me give you the value. It's 5.72 times 10 to negative 2 radians in the clockwise direction. If you convert it to degrees, it would be 3.28 degrees. Again, in the clockwise direction. Yes.
Is clockwise always positive?
It's a choice. It's a choice. So if it's just one, then stay with it. If there are two, the same thing. Pick one, stay with it. Later, we switch to counterclockwise. But for this one, didn't happen.